Hi there, this is Robin Andrews from Comp Academy, and this is a video about producing sound with Python. Now, this is something I've been trying to get together for quite a long time. In my youth, I used to spend a lot of time playing games and also writing code on home computers such as the ZX Spectrum, BBC Micro. And they had some great features in terms of making sound that are actually quite hard to reproduce using modern languages. So I spent some time trying to get this to work, and I've finally done it, and I wanted to share it with you, okay? So I'm first of all just going to play this so you can see what it does, and then I'm going to talk you through some code. Okay, so let's run it. Okay, so what you have there is a minor natural, A natural minor scale, same notes as C major, starting A, B, C, D, E, F, G, octave A. And it's produced using some stuff. So one of the things it's using is a module called Simple Audio that is not part of standard Python. So you're going to need to import that. Importing modules is a skill you basically have to have if you want to do anything beyond the very basics in Python. I'll just show you that now. If I open up PowerShell, which you can get from the Start menu, just type in pip install and then the name of the module, which is Simple Audio. Okay. Now I've already got it, so I'm not actually going to hit enter, but that's all you need to do if you've got a standard installation of Python. I'm using Python 3.8. Then everything should go fine with this. Okay. If not, then that's another topic. But you basically need to be able to install modules in Python. So this is a good place to start if you haven't done that already. So we've got this module Simple Audio. Then we've got a constant defining the sample rate here on line 4. Now I've used an incredibly low sample rate for any kind of real audio, such as CDs and that sort of thing. You'd have much higher sample rates, such as I think it's 44,100. Yeah, 44,100 hertz. This is in hertz, okay, but 8,000 is fine for our purposes because we're not trying to produce, high fidelity audio here. And then we also need this other module called numpy, okay, which is another external module, third-party module, but it's a very, very common one if you want to do any kind of scientific computing or any kind of heavy mathematical calculations, including what we're doing here. Then numpy is a very, very useful tool, and it's good to be aware of it. So yeah, we've got these imports. So numpy is available as NP and Simple Audio is available as SA. And then we have the function here, get sound. Okay, and what this function does is it creates a wave object, okay, which can then be played back by the Simple Audio module. And it's basically manually generating a sine wave using some mathematics. Now, you don't need to go too much into the mathematics, but I'll just talk you through a little bit of what's going on. So we have a time vector. This is basically just time intervals. So say the sound wants to be 1 second long, it's splitting it up into 8,000 slices, okay, because we have a sample rate of 8,000. And then we have some way of converting the parameter that's given for the note. We convert that into a frequency. So a very, very useful formula to know, even if you don't necessarily understand how it works, is how to convert piano keys into frequencies. And we're using this formula here. So the principle is if you double the frequency, you get an octave of the same note. So the 12th root of 2 is going to be the interval for each semitone within that octave. Okay, so that's basically how that works. Later on, we're going to look at smaller divisions, but we'll come to that in a bit. Okay, so we've got this formula for converting piano notes into a frequency. And then we create a whole bunch of values for the sine function, okay, and then we amplify it, okay, so we multiply it by, this is the biggest 16-bit integer available, biggest value for a 16-bit integer, positive, okay, so that's kind of maxing it out, but we're also taking into account the volume, so we have the ability to, have louder or quieter depending on this argument on line 7, which is set default 0.5. By the way, turn your speakers down before trying this, okay? Because you never quite know how loud it's going to come out. You don't want to hurt your ears or blow up your speakers. Okay, then we've got this issue to do with clipping. So if you have a loud sound and it drops off suddenly, you get this weird clipping effect in your speakers, and it doesn't sound very nice. So in some cases, we can save that by kind of getting our basic sine wave. What's a sine wave? And towards the end, we kind of fade it out. Okay, that's what we're doing. We're still doing its sine thing. Like I say, there's some maths and physics going on in the background, and it's really up to you how far you go with that. The function just works as provided, and I will provide this code in a paste bin or something. I might even do a blog post. It's quite interesting, but also it's a little bit daunting if you're not used to that kind of thing. So you can literally just use the function as is, but I'm just talking you through it. So if you get stuck, you know where you need to look to change things and fix them. Okay, so we're, fading out the sample towards the end. And then we're just returning, it's basically a numpy array, I think, that gets returned, if I remember rightly, which we can then use to play sound, okay? So we do this for every single note we want to produce. So then on line 28, I've used a list comprehension to produce samples for each of these notes in the A minor, Aeolian or natural minor scale. Okay, so piano notes 49, 51, 52, 54, etc. Okay, and then I've gone through that list and I've basically created a wave object, line 30, and then I've played the wave object, but I've given myself basically a handle from that, okay, so I can access that play object so that I can tell it to wait. Okay, if I don't do that, if I don't do wait done, let's just comment that out a minute and run it again. You'll see you get a different effect. Okay, it's quite nice. It's like a arpeggio, but that's because it's starting the next note straight away without waiting for the previous one to finish. Okay, so in most cases you probably want to have wait done at the end. Okay, so obviously that's just a starting point. It took me a lot of research and a lot of work to get to this starting point. So you guys are having a head start with that. Basically, you've now got the ability to throw in piano key values and play them in different sequences. You might want to get into some like algorithmic composition, so maybe some like random numbers or random within certain constraints or whatever. I mean, it's a big world to get into, but that's it's a kind of starting point for you. However, back in the day with BBC microcomputers, we didn't just have semitones, right? The BBC Micro, I believe I'm correct in saying it had 4 gradations between each semitone. Okay, so if you get a semitone and you cut it in half, you got a quarter tone. If you cut that in half, you got an 8th tone. You cut that in half, you got a 16th tone. So you were basically talking at the level of 16th tones. Okay, so between every piano key, between like a white key and the next black key, you'd get 4 notes between them. Yeah. And the way we do that is we look at if you look here on line 9, our frequency formula, we change it a bit. Okay, so I'm now going to comment out the kind of nice sounding equidistant piano frequencies one, and we're going to do something a bit more crazy here. We're going to have those, many more intervals within the space between semitones. So this is the formula now. I've taken A, okay, I've halved it, so it's like quite a low A, so it gives us a bigger range. And then I've raised it to the power of 2 to the power of the 48th root. Okay, correct in saying. Like I say, if you're not into music and mathematics in general, just don't worry about that. Just understand it gives you a lot of notes that you can play with, which is great for doing effects, all right? So you remember these silly effects, like what's his, a manic minor or whatever, he jumps and it goes, okay? So you have these tiny little gradations of pitch that you can do that with. So let me show you what I mean. Okay, so let me just explain what I've done here. I've got my blips, okay, are a list comprehension consisting of a whole bunch of values got from get sound. Each one's going to be 0.1 seconds long, and the frequencies we're going to pass in are going to be between 48 and 144, and we're going to do it in steps of 3. Okay, so you're never going to hit, well, very rarely going to hit a note that's actually on the piano when we do this, but that's not the point. I want to show you this kind of effects potential for this way of doing things. So let's run that. Okay, remember manic minor jumping, and of course you can come down the other way. Let's quickly show you how you would do that. So one way you can reverse the list is using the alien smiley technique. It's : -1. Now it's all to do with list slicing. Don't worry about why it works particularly, but let's do that now. So on the way up, and we should do the same thing in reverse in a minute. Okay. Okay, so that's not bad really in terms of retro sound effects. We've, you know, there's a lot of potential here. There are a few restrictions. If we get too short on the sound samples, for example, I think I've managed to get down to 0.02 and they're still audible. 0.02. So let's try that. Okay, that really does sound like Manic Miner. If you don't know what Manic Miner is, it's a game that many of us of my generation spent many hours playing. It's like one of the original platformers. You had to go and collect I think it was the glasses from after a party in a mansion, and there was all these dangers on the different levels, and you had to jump over them and all stuff. It was a great game actually. So yeah, that's how it's done. So yeah, retro sound effects. I mean, the world is your oyster, really, with this. Like I said, I've given you this massive range of frequencies, even between the semitones. So you can do all these kind of, you know, blippy effects, like, you know, climbing, falling sounds. Obviously, you don't have to use all of those intervals in between. If you were to, for example, do it in steps of 4, this would then just become normal semitones, right? So actually, let's just show you the tiny gradations, because we weren't doing those, were we? So let's do it in steps of 1. You see there's a little bit of trouble with the processing. It's like not completely smooth in terms of time. Let's give it a slightly smaller range. So we'll just do, I don't know, 48 to 92 or something. 92, and slow it down a little bit so it's longer samples. Let's do 0.1. Okay, let's try that. You can hear that tiny increase, yeah? Okay, so I'm showing you like the nuts and bolts here. I'm not getting into the whole kind of creativity side of it and musicianship and that kind of thing. There's loads of techniques you can use, loads of patterns you can explore, maybe some kind of like looping in terms of the frequency or something, so it kind of reaches a certain point and then comes back, maybe using the modulus function. You can even tie it in with animations, maybe using some turtle graphics or something like that, or, you know, whatever idea you have, just explore it. That's the thing with this. It's like creativity. Okay. Fun with computing, fun Python. It's what it's all about. You know, life's a bit stressful sometimes, so if you can have some fun along the way, then so much the better. So there it is, folks. I hope that was useful. Retro sound effects in Python, stage 1. I'll probably be back with more. In fact, I'm going to integrate some of these effects into games as I share games, like, you know, Pong. You can have the ball making a noise, or Snake. You can have like a different noise for each direction, that kind of stuff. There's all sorts of possibilities, and lots of fun to be had. Okay, so thanks for watching. Don't forget to subscribe, and I'll see you in the next video.